Okay. So, another thing that you probably will notice, and it's been pointed out that I tend to do this as well, and that is I forgot what I was going to say. That I tend to jump around, and not often do I have a cogent stream of thought or presentation. But why did I want to say that? I don't know. So one of the ways, I guess, of presenting material is to have it written in front of you. And you might go to professional conferences and so on, and you'll have a speaker that has prepared text. You know, they have it's all written down. And what they do is just read it. They look at the paper like this, you know, and they read it all while you're sitting out there watching this person. Boring, right? I think to some extent the speaker himself or herself needs to be enthused enough and driven enough to almost be able to improvise. And I tend to do that quite a bit. Because it's not exciting to me, and I don't want to be bored here. But it's not exciting to me to just repeat the same thing that I've been doing. But that comes at a peril anyway. And the peril is that the innovation or the new approach that I run across, so that I don't do the same thing exactly the way I did it before, is that it may be a little bit disjointed, because I have to make up the joke on the spot, and it may not work, or however. So the material that typically I will present, I might have brushed up on it the night before, but it'll be, to some extent, I can almost guarantee you, an impromptu presentation. And I'll try to make as fluid a presentation as I can. So where do we start in this whole process? The objective, underlying objective, from a technical point of view, to high-speed photography, particularly high-speed photography, is measurement. You want to know all kinds of things: how long things last, how fast they move. No, I guess that's about it. I'm not sure what else there is. How long they last, how fast they move. I think that covers it. So one might want to, if that's your objective, you might want to think a little bit about what makes measurements possible. And there are many tools that we use for measurement. That one. The clock. There is a clock. And the question is, it reads out time in seconds. Well, do you know why a second is as long as a second? Why isn't a second longer? Oh yeah, that's one thing I was going to say. Talk to me. I'm more than happy to listen. Yeah?
Someone said so once and it's stuck.
Exactly. Someone or a group of people said, that's how long a second is going to be. Maybe they might have started with an hour, they might have started with a day, and said, well, we're going to break it up into pieces, and etc. But there is no magic, there is no rule that says that a second has to be a second. And that same approach, or the same concept, is behind just about anything. Anything that we measure. well, in relative, well, no matter what, I was going to say, well, there are some things that are absolute. Well, I don't think so. I was going to say something like the wavelength of light or something, or the wavelength of some isotope or something. But somebody has to say, well, we're going to look at 10 of them, and they're going to be this long. Okay. But somebody says, well, it's going to be 10. Well, why not 11? I like 10. Or whatever. The whole concept to this is that a group of people establish a standard. Without a standard, measurements are out the window. This is true in finance, economics. I'll trade you a donkey or a pig. So, the same value. Maybe a donkey is worth 2 pigs. I don't know.
What if your donkey's a crappy donkey?
Yeah, right. Yeah. So you have to have a standard donkey. Right? So it's, the same, I'll give you this coin for whatever, and this stands for so much. If you don't agree, then everything comes to a standstill. So, where are those of us who use image-making equipment affected by a measurement? Well, in many cases, distance to an object, in feet or inches or millimeters or whatever. We're affected by. Well, there are a couple of things. If I remember this. I think. In photographic terms, what's H stand for, anybody? Exposure. And what does this stand for? Time. And then, therefore, this stands for what? Intensity, luminance, energy, the amount of light that falls on something, right? So, this is sort of analogous to, a water faucet. Water coming out of it. You can fill a bucket by opening this, and it takes you some time. You can fill it faster, you can have a bigger faucet, or you open it more, or whatever. So you can either booger up this, or you can booger up this. And if you want to, in order to keep this constant. So, in this photographic world, we are concerned with time. And we control that with the shutter of a camera. Shutter opens, closes, and that then controls the volume that we end up with at the end, given that the light level is constant. And we kind of ensure that, kind of, sort of, by the way, by setting an aperture. But of course, that deals with how much light we have to begin with. But assuming that we don't question the aperture, the other control is time. And to get a good result, we want to make sure that the time is right to get the proper exposure. I'm not sure how that works out in the digital realm anymore, because it turns out that I'm not sure how many people are actually concerned with exposure. Push the button and look at the picture there. If you like it, you keep it. If not, you don't toss it. But from a technical point of view, you want to be able to predict what exposure is. It opens up avenues for measurement later on. And so we take our cameras and they come equipped with some kind of a light interruption device. These days there are a number of them, taking different kinds of approaches. In the traditional sense, they're there was this kind of a shutter, an opening that was inside the lens, typically. And it consisted, it still does, of a set of blades that separate from each other and then they go back towards each other. And they're set up in such a manner that they can overlap and extinguish the opening totally. So it's not like a diaphragm. A diaphragm, you can't get rid of the hole. Now let's see, this one here. Right, there it is. Okay, so there's a diaphragm in operation, but you can't eliminate the hole. That's because those blades are supported on two opposite points, and the blades go in between, and you just can't extinguish it. The shutter blades are also connected on 2 points. However, they're close to each other, and they drive a large blade, and that overlaps the other ones. So the function of these is to control time. Now, what about another kind of shutter? Traditional, the two traditional shutters are the between the lens shutter, or leaf shutter. There are a couple other names for it, I forget. And the other option, traditionally, was and still is, the focal plane shutter. I like focal plane shutters. So a focal plane shutter, the very first one. It's over here. This consists of a couple of rollers, top and bottom, and they are connected by a curtain. You can imagine that. So it's just a curtain, and it's got slots in it. And I'll take a look at one. Oh, there's one. Draw that. It's supposed to stay up. No, I don't need to do that. Well, I needed to do this. So you'll get to see more and more of the camera than you probably wanted. It's taking too much time. I don't want to lose the time. Unfortunately, I'm going to waste your time. All right. You hidden. So there is the biggest slot in that curtain. Now you can roll it up. Okay, and it stays there. And now you go to the next one. Notice that it's a little smaller. Right? And you go to the next one, and it's smaller yet. And you go to the next one, and it's the next one. I wonder if there's another one. Maybe that was the smallest. Oh, there's the smallest one. So how do these things work? Well, there's an opening there. The light comes through, puts an image on the image plane, and you let that shutter go. So the slot moved down. So it uncovered the top, and then later on uncovered the bottom, exposing the whole image plane. Well, this dates back to the long way back, probably 1800s. The problem with these, well, the big advantage of these is that you can get a very short exposure time, because you control exposure time by how fast the slot moves and how big it is. So if you want to get really short exposure times, you just make this slot really fine. Now it comes with a trade-off, okay, but you can achieve speeds of, these days, I'll talk about those, the electronic ones, a thousandth, 10,000th of a, even a 10,000th of a second by making the slit finer and finer. Another way to do it is to make it go faster and faster. But if you make something go fast, in that case you got to stop it too, right? And eventually, if you go too fast, that thing breaks. Yeah, that's no good. So there are mechanical limits that you can reach. But then the other thing that you may have noticed, probably not, is that the slot, because it's driven down, accelerates. So it goes faster and faster. Well, since exposure time is a function of how fast it moves and what the size of the slot is, if you keep the slot the same size, the exposure time will be different on one side of the image plane than the other. Well, that's no good. You want the exposure to be the same. Well, for that, this shutter was developed, and in fact, this kind of shutter is used in cameras like that too. So this one, when you wind it up, you don't see a slot. But it is made up of two curtains, just like, oh, it's made up of two curtains, whereas this is just one curtain. And then when you let it go, in that case, the first curtain goes down, and then it's followed by the second. And you notice that as it goes down, it opens up, right? It's pretty cool. It does it automatically. So as it increases in speed, it also gets bigger, and that means that the exposure remains constant from one side of the frame to the other. These cameras, the digital ones, not all, but most of them, have a focal plane shutter just like this one. Two curtains, let one go, let the second one go, the distance between them increases a little bit to keep the exposure constant. Now, why have shutters like this one, even in that camera? Because they allow you to change lenses, MOP coverage, without having to change shutters. Okay. For this, you put shutter and never lens. For this, you just have one shutter. That's kind of neat. Now, what about the digital cameras? Well, as I said, most of them still have shutters like this one. However, there are variations in the digital ones where shuttering is accomplished by turning the pixels on and then turning them off. Essentially, you're talking about a gazillion light meters in there, right? So you have a gazillion switches, and they turn the light meters on for a little. Oh, light meter. Anybody know what a light meter is? You know, they've gone by the wayside too, haven't they? Oh, to a large extent. Yeah, but that's exactly what the name implies. They meter light. It's like a water meter. Well, not exactly. So there are these light-sensitive gadgets there. You turn on a switch, they turn on, they start to collect light, and then you turn it off, and they turn off. And you can do this in a couple of different ways. For a digital system, you can turn them all on at once, then turn them all off at once. Or you can turn them off a line at a time, or something like that. And they mimic, in that case, if you look at one digital line at a time, they mimic these shutters pretty much perfectly. Now, why are there these two different kinds of shuttering mechanisms in digital cameras? Cost, typically. It's cheap, and you'll have more of those. But the big advantage of the ones that can be triggered on and triggered off is that they expose the whole image at the same time. Almost the same thing as these shutters do. How should I say it? Actually, the same as these shutters do, except that the digital version has a much faster response time. Now, if you set this to some speed, you know, it takes time for it to open, and it takes time for it to close. Well, that little time that it takes the shutter to open and to close can affect the appearance of the edges of moving objects. You want a shutter that is called a square wave shutter. A shutter that goes, time goes like this, and you go boom. It's on, stays on, boom, closes. Very few shutters, even these, don't quite do it. But they come very close, whereas these are quite far away from that. And so, what's the other disadvantage of these shutters? Well, it is that they're scanning shutters. Like you saw, it exposes the top and then the bottom. What's the consequence of that? Well, if you're photographing moving objects, and let's say that, and forgive me for this, I'll use a traditional shutter design. Why? Because I'm used to it. And that is a horizontally moving shutter. By the way, do you know which direction your shutter moves in your digital camera?
Up and down.
It's a cheap shot, right? It's because they just about all do. Yeah, they all do. Does it move from bottom to top or top to bottom?
I think it's top.
We'll find out. It just says, how acquainted am I with my camera? Right? Or do I just push the button and, oh, the shutter did its thing? Well, let's just use a horizontally moving slide. Let's say that you're photographing something like a light bulb, a fluorescent tube like this. And the shutter's over here at one time, and the fluorescent tube is over there. Well, they move the shutter. And the shutter is over here at some point, and that's all covered up, okay? And that's all covered up. And here's an open slot. So this relationship between that image and that shutter exists at this time. The shutter moves that way, this moves this way. So by the time the slot gets to this side, the bar is down here. Okay? The image of the bar is down there. So what's the result? Well, you end up with an image that looks like this. And then you, in your technical wisdom, said to your supervisor, I photographed this thing that was kind of tilted like this. And, it wasn't, right? It came down straight. This is an artifact of the scanning nature of focal plane shutters, and it's also an artifact associated with the scanning nature, typically, of CMOS sensors. One is called, when it all opens up and closes down, I think it's called a global shutter, and otherwise it's called a rolling shutter. I'm not sure why they call it rolling shutter. Well, I know why they call it rolling shutter, but it's well understood in photographic history. This is focal plane shutter distortion. In their case, they don't have a shutter that moves, they just have the scanning of the lines that moves, but the idea is the same. Things get reinvented and put the word digital after it. This is not rocket science. It's been known for a long time. So there are advantages to the global shutter. There are advantages, cost-wise, typically to the rolling shutter or the other one. But ultimately, they all control time. So, since we are, you turn on the camera or any one of these, you look at this, typically you're told, the manufacturer's gone to great pains to stamp on or put on an LCD or whatever, what the exposure time is that the camera's delivering to you. That's useful for whatever application you might have in mind. Not only to generate the correct exposure, depending on what kind of imaging you're going to make, you want to choose a particular exposure time, and we're going to do more about that next week. But you're not operating blind, so to speak. Manufacturers go to great pains to give you timing information. The question is, in our context, trust what they tell you.
No.
You would hope that you could, right? But not necessarily. I'm not going to, well, I will, make an analogy with the internet. Everything you read on the internet is not true. You'd like to maybe think that it is, but people make mistakes. All kinds of errors that creep in. Maybe not so much in the digital world anymore, because you have more sophisticated timing systems, but in the analog world, in the mechanical world, there were discrepancies that were associated with exposure time and shutters. We're going to ignore the fact that things are better now than they used to be, and we're going to go through the exercise of standardizing, calibrating our cameras against a standard. So it's going to be like that tomorrow. I think, not sure if you all go back far enough, but this was also an exercise to some extent that was done in MMP, at least partially. I remember because I set up the experiment. But neither here nor there. So if you're going to calibrate something, you need a standard to calibrate it against. What can we use as a standard to calibrate this shutter? Maybe a clock. Yeah, that would work. If the time that the shutter would be open would be long. But if the time is like so, trying to figure out how long that was open for is kind of difficult. And so we need a better standard than something that will track what that shutter is doing faster. Well, the notion here is that we're going to use a standard to calibrate our camera shutters against. And then we'll be like the National Bureau of Standards. Well, they have some standards. And you calibrate your instrument against theirs. They have a standard. So we're going to calibrate the camera shutters against the standard. And where might that standard come from? Well, an inexpensive standard, and just to get an idea of how the concept behind the approach to calibrating a camera would be to use a readily available standard. There are many industries that operate on standards. The plumbing industry, for example. I'm not sure what made me think of that, but you know, they have standard fittings, so you're going to have those if you're going to go someplace. So, but there are two industries in particular that you interface with on a regular basis that are based on easy to understand standards. One is the audio industry, and the other is the video industry. Right? The audio may be not so evident right now, and even I guess the video or whatever. I guess even using the word records these days, but that's not actually true. I was going to say it's kind of obsolete because people talk about vinyl. I'll just say vinyl instead of a record on an LP. And you know what I'm talking about, right? It's a record player, and it's got a disc on it, and it rolls around. And somebody, okay, put some grooves on it, put some marks on it, and then when you run those marks against some other instrument, lo and behold, out comes sound. Changing audio input to a mechanical output, and then that mechanical output drives another mechanical output, which then drives an electronic audio output. So the record industry depends on you playing the record back at the same speed as it was designed to be played back, which is a standard. The vinyl is still a standard, and it rotates 33 1/3 RPM. There are offshoots of this, of course, you know, CDs and so on. They rotate different speeds. Who cares? We're more interested in the concept than the specifics of it. But a record, typically, you know, for many years now, has been rotating at this speed. There were faster ones. Not going to let rotor. Now this can be easily transformed. RPM is an okay number, but degrees per second might be better. And if we take this, multiply it times 6, out comes 200 degrees per second. This means that if we take a look at a disk and put a mark on it, and we start to look at it at some time, and then we stop looking at it a second later, that mark will be someplace over here. Right? 180 to there and a little bit more. Now the neat thing is, I mean, this would happen in front of your eyes, okay, if you do that. But in our case, if we're going to make measurements, we're going to make a record of where this is, at the beginning of time and at the end of time. Well, an imaging device works just right. Something that will store information. So we aim our camera at this disk, and when the shutter opens, the mark is over here. And when the shutter closes, it's over here. But in the meantime, it was in every other place. Okay? So it moves from here to here, and it leaves a track. It leaves a blur. And that blur is an indication of the fact of what that mark did over time. Ultimately, all you need to do is to measure the arc. And then the exposure time is going to be what? Arc size divided by 200 degrees per second. Right? This is going to be in degrees, so the degrees cancel out, the seconds move to the top, and you end up with the right units. This is the concept. And it works because the imaging device is going to start to sense an image, presumably instantly. So, carrying this just a little bit further, just thinking-wise, if we measure 100 degrees, 200 degrees, so that's equal to 1 second. 100 degrees, a half a second, 50 degrees, a quarter of a second, and so on. But this is the operating relationship. So we're going to make this a little more practical. And that is, I've just drawn that from scratch. We're going to put a mark here. A piece of paper with a little wedge type thing. I'm not sure why make it a wedge, but let's make it a wedge. So there it sits. And at the end of the exposure, it's sitting over here. So it has moved all the way from here to here. And now, you say, okay, I'll measure the mark. So you put a protractor here, and you measure that. And you say it came out to 200 degrees. And you make a deduction as to what the exposure time was that caused that arc to happen. But there's a problem in the measurement. What is it?
You measured from the beginning of the wedge to the end of the wedge.
You gotta remember this. Beginning to beginning, end to end. If you measure from beginning to end, you include the object itself. And in a measurement, you have to remove that in order to be a little more precise. Now, over a 1 second period, that may not make much difference, right? So supposing that you start out with an arc here that's 10 degrees. Now instead of 200 degrees, you're actually measuring 190. Well, the difference is not bad. Is it 5%? However, if you choose a shorter exposure time, okay, where this moves only that far, and you measure this, and it turns out to be 20 degrees, and you don't make an allowance for the fact that you had a mark that was 10 degrees to begin with, well, now you're saying you were supposed to read 10, but you read 20, so that's what, 100% error? Or sometimes you get my percentages. Often I get my percentages for good. But then you operate on gut feeling. So you were supposed to get 10, but you're reading 20, so that's 100%. If you read 20, it would have been a tenth of a second, right? Because it would have been 20 over 200. Oh, that's a tenth. However, it was actually 10 over 200, and that's a 20th. So a 20th is half as big. So it's how much the percentages when you're talking about fractions and so on get kind of messed up. But this is half as big as this is. So you're reading 100% increase over what it actually was. It starts to make a difference at the short speeds. So we can modify this by saying the arc size minus what it would be stationary arc size. So we subtract out whatever the beginning arc is. And using this approach, you can make measurements against a rotating turntable, probably fairly reliably. And what I'd like to do is to do that from 1 second to 125th of a second, or something like that. Okay, so you have a little lookup table or table, and it says 1 second to 125, and underneath you put the measured speed. This will be maybe 9/10, and the next one might be 4.5 tenths or something like that. Probably in decimal form, 0.9, whatever, 0.45, etc. Once you have a chart like that, then eventually what you'll be able to do is to plot this as a series of errors from aim. And so you have your speeds over here. This would be 0%. Over here you have 100% plus. This would be 50% exposure. And then you can plot these up and down and so on to make a performance graph of what the shutter does at the speeds. You'll get more information about this with time. Somewhat, another concern is, if you're going to be thinking tech, is that you have this disk, and you'll have a shutter moving from here to there, or from top to bottom. It doesn't really matter. And if you, what I'll do is this instead. I'll make this just a little smaller, so I'm more comfortable with it. It's an image of a ball. And I'll probably mention this again, so I'll mention it now so that I can later mention it again. And that is that I have sort of a pet approach to imaging and image making. And that is, if I look at this, look through the viewfinder, and I aim it towards you, I might ask myself, Andy, what are you looking at? And I'll say to myself, I'm looking at you all. I make an error. What is it? my pet peeve.
Aren't you looking at a mirror that's reflecting the image up to the viewfinder?
I'm looking at what?
A false image?
An image.
Yeah.
Not a false image, it's a real image. But I'm looking at image, I'm not looking at you. It's almost the same thing as when people share, snapshots with each other and say, oh, look at that, there's Susie, look at her big smile. No. You're looking at a photograph of Susie, right? Not at the girl or the guy. The boy named Sue, right? So, I think it helps in the imaging field to forget, in a way, or when convenient, forget reality. Because what you're really dealing with is the images. The light that is formed there by lens. And that interacts with the shutter. And that interacts with your sensor. And you say, well, so how can I deal with that stuff out there? Well, there is an optical connection between the two. Magnification. You allow for that, and now you're dealing with the subject. Most of the time that works better than to try to think about what the subject did. Think about what the image did. So anyway, here's this image of this ball, and the ball is going to be moving that way. And the shutter is going that way also. Well, let's say that the shutter is moving slower than the image of the ball is moving. So then you look at the result on your camera, and what do you get? Very good, nothing. Because the shutter never caught up to the image, right? So, but supposing that the shutter moves faster than the image moves, and it passes it, in that case, what's that ball going to look like? Yeah, elongated. And the elongation will depend on what the relative speed between the two is. If they match, well, I want you to think about this. Suppose their speeds match, what will the image look like?
Has it already caught up to the ball?
Right? Because you won't see the beginning or the end. You just see whatever locked in, and that just wipes across. So this is something to consider when you're dealing with focal plane shutters. Whether it's a shutter in here, whether it's a rolling shutter in the digital realm, or whether it's a focal plane shutter like in these cameras. So in our case, we do have image motion during exposure. And where does that come from? Well, there is this mark, that there. And over here it's moving that way. Here it's moving that way. And if we have a shutter that is going to move that way, in one case this is going to be stretched out. Right? In the other case it's going to be compressed because it passes over it faster than if it was standing still. So from a thinking point of view, and not that it's going to make any difference in your case, but from a thinking point of view, the time that you want to be making the photograph of that moving mark, exactly, is when it's here or here. Because there it won't be stretched out or compressed. Not as much as it will be here or here. Just something to keep in mind. So now, we're going to say, well, you can do up to 125th of a second, and why can't you do less than that? Well, because the arc starts to get way too small. With protractors and so on, you might measure accurately maybe to a degree. And once you start to talk about less than that, forget it. It's like trying to, I can't think of it fast enough. Using the wrong standard to measure something. I guess you have a yardstick, and you want to measure what the length of this peanut is, right? Well, using the wrong measuring tool. So, but now we say, okay, 125th of a second is max. And how do we go faster than that? Cameras can go faster. Well, we rely now on the video industry. The video industry has changed quite a bit, and I must admit, I'm not up on the latest and greatest LCD displays and so on. So I'm going to rely, and because I have available, I'm going to rely on old-fashioned TV. CRT tube, and the way that works is there's some kind of a display. Back of it, there's a tube. Back over here, there's an electron gun. However that works. It squirts electrons. It's peeing on the thing. Careful, Andy. Somebody's going to object to this. I hope not. I hope not, man. Life would be boring. So anyway, here's this thing, you know, and it's energized by magnets. It's got a magnet on the top and bottom and side to side. And they're synchronized with each other in a particular way. One side to side cause the electron beam, okay, to move across the face of the screen. And the other ones cause the height of that scan to drop, or to get lower and lower, until it gets to the bottom and it starts at the top again. So there's a ratio by which these two interact with each other. This horizontally, it scans 262.5 times. And then this says, oh, drop one line. No. That's not what it is. I'll do it this way. This isn't totally incorrect, but there's a little glitch. It takes this line, 1/15,750th of a second, to go across the screen. And once it's gone across the screen, then it comes down one line. It goes across the screen, comes down another line. It does 262.5 of those, and then it goes back to the top. Theoretically, it goes between the first two. And then it does 262.5 more. At that point, it refreshes itself. Whatever information it had about what the strength of, oh, by the way, how do you get an image over here? Well, you get it because the harder the stream of electrons hits the screen, the brighter the screen gets. So you modulate the intensity of that beam with how strong the magnets are, and that gives you shades of gray. So if you were doing a box of some kind, well, they go to here, and then, whoops, it would go to here, and then would be a blank space there or whatever. And then it doesn't have to be a blank space, it could be a gray space, depending on how the beam is controlled as it goes across. It's pretty much magic. But anyway, it does 262.5 lines in 1/60th of a second. And then it does another 262.5 in another 60th of a second. And then it refreshes itself. That's a total of a 30th of a second. So every 30th of a second, it puts a new picture on the screen. Every 60th of a second, it puts half a picture on the screen, so to speak. The total number of lines for a single image is 525 in 1/30th of a second. And that's where this comes from. 15,750 lines every second. TVs work with a standard. Not sure what the current standard is, but in Europe it's slightly different. But that's the idea. So, how do we take advantage of a television set as a standard? Well, we take the TV and aim a camera at it. It has a shutter in here. And whatever this is going to move across. So the sensor is going to respond to the brightness of that spot on the screen. The spot keeps moving. So let's get rid of this for the time being. We'll use a camera that instantly is available to record. So some instant, that spot is right here. back to here. And the rest of the screen is dark because it hasn't been lit up. So this is the same thing as that moving arc on the turntable. So then you, and you adjust the aperture and the speed or whatever it is so that you can see that image. It would not be of use if you didn't see it. But then you examine this. You say, oh, look at this. I think that what this did, it started here, went over to there, came down here, dropped one line, and it came back, and then the exposure was interrupted. You say, well, in that case, how much time elapsed? You could do a couple of them. One of them is just use logic and say, well, 1/15,750th. Oh, come on, Andy. 750th of a second. That's just using gut feeling. The other one is to say, well, here it was standing still. How many lines did it complete? That's 0, 1. Right? So you say exposure time is equal to the number of lines divided by 15,750. Right? So you say, okay, well, I don't have this. My picture looks like this. And it goes to there. It goes to there. It goes to there. It goes to here. And it goes to here. Well, what's that? Well, you do the same thing. So 0, 1, 2, 3, 4, 5, and 5 1/3. Divided by 15,750. I don't know what that is. It's like what? 2,500th of a second or something. Anyway, that's the concept. Now, in this case, we were assuming one of the digital global shutter. But if you use a focal plane shutter, in that case, now you have to somewhat worry about the fact that you have a shutter slot that is moving. And most of you don't have a global shutter, not on an SLR. On some of the CCD cameras, I'm not even sure about that, so I'm not going to go out that way. They can come in many different configurations. So, but with a focal plane shutter, the shutter could be moving with the scan. It means it starts to expose here, but by the time it gets to here, this has gone further than it should for the exposure time that the shutter actually delivered. So what you want to make what you'd like to do in order to keep precision as best as you can is to make sure that the shutter moves perpendicular to the scanning direction of the TV screen. So if it's a camera like this one, all of them, camera goes vertical because the shutter is going to move this way. Or the other way to do it is to turn a TV set, whichever. And turn the camera just as easy. Now, what this is going to cause is when the shutter moves perpendicular to the scanning direction, the pattern here is not going to look like this. Think about it. Wow, I don't have much time. Oh well, you can read about it. I'll send you some material. The shutter goes this. Oh, sorry about that. Well, we're going to get it this way. The shutter is going to move side to side. The scan is going to go top to bottom. So what happens is you catch the beginning of it, let's say here. It goes to here, comes back to here. And by the time the scan line, 15,000th of a second later, gets back to here, the shutter has moved over just a little bit more. Okay, so it used to be there. This time it's over here. And then it starts, it goes back to here, And instead of stopping there, it goes a little bit further. So the consequence is that the edge of that pattern is going to be a diagonal like this. Like that. Now from this you can learn all kinds of things about what the speed of the shutter was, if you calibrate the system. And the other is that make a pattern that looks like this, and all it says is that the shutter was open this much, okay, during the exposure time. The longer the line is, the bigger the shutter opening was. And you can actually, to a very good approximation, determine what the shutter width was for any given exposure time that is less than maybe a 200th of a second. At 125th of a second, the lines are going to be very long. At a 60th of a second, well, they're going to fill the screen from one side to the other. But you may still get an edge like this, and that is because a 60th of a second later, the second part of it is going to be touching the first part, if you're exactly accurate. Again, you still, to determine exposure time, you count the total number of lines in this pattern, and you divide by 15,750. That gives you the exposure time. Now, if you wanted to find out what the width of the slot is, in that case, you make this, you scale it. You say, well, on Photoshop or something, you make a measurement with the ruler saying, well, I know that this frame is so wide or whatever it is, and then you can measure this in millimeters. The neat thing about this, if you do this, is that you can then correlate, let's say, 1,000th of a second, 500th, and let's say 250th. And supposing that at 1,000th of a second you measure one of these lengths and it turns out to be 6 millimeters. What do you think that the length should be at a 500th of a second? Anybody? About 12. And what about at 250th? About 24. This says that as we double the exposure time, the slot keeps doubling in size. We're not changing its speed. You'll notice that the slope of this remains constant. It's just the length of the lines gets bigger. So, what I'd like you to do to complete part of this is to go from like a 60th to a 1,000th of a second using the television set as a calibration device, assuming 15,750 lines per minute, lines per second. So that's our standard. Okay, now one more thing. That is, wouldn't it be, at one point, I was going to say, well, wouldn't it be nice if there was some other standard? Well, thinking way back in distant history, there were, improvised methods for calibrating shutters having to do with fluorescent tubes. Well, what's so special about fluorescent tubes? They cycle. Yeah.
I've got to get to them in class.
That's fine. They cycle like this. Okay? They go up and down 120 times a second. There's 60 cycles. Okay? There's 60 cycle current that drives them, but they light up at the top and also at the bottom of the voltage pulse. They go 60 plus, 60 minus, and as they light up here, they go 120 times a second. That's pretty cool. So how do we use that as a timing device? Well, you take the camera, take a television tube, whatever, and you sweep the camera so that the image of the tube goes across the focal plane of the camera while the shutter is open. And then you count the number of pulses that you see. Well, we're not going to use a fluorescent tube because these are now going at 400 times a second, and they don't have very good resolution. Instead, I will provide you with an LED flashing light source that I made. It cost about 50 cents. 56. And it flashes. And I made it so it would flash 100 times a second. Now, some people say, well, think about it. The think about it part is that if you have something that flashes at a, you know, it's like decimals. Decimals are much nicer than feet, right? Flashes 100 times a second. That can be a nice, useful timing device. And in photography, all you got to do is photograph that flashing light. So you put the flashing light here someplace, or you move it. So you know, there it is. It's flashing, flashing, flashing. You put the camera over here, however, and you sweep the camera so that the image of this lamp moves across the focal plane, and you make sure that within your frame you don't have the dots moving off your frame. So, you know, as you sweep the camera, then you look at the image and say, oh, well, I'm not sure in this case. I think you count every one of them. It's a point of argument. Maybe you want to correct me on that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 5, 10. So you count 10 of them. You say, oh, okay, well, how long was the shutter open for? Well, it was 10 flashes and 100 flashes per second. Per second. Yeah. So it was open for 1/10 of a second. Kind of neat. Did I do that right?
Wouldn't it matter about how quickly you sweep it across? Wouldn't it matter how fast the camera was moving?
It's actually a good point. As long as this is flashing. No, that's right. But aren't you in luck? This is an LED-driven light source. And it's essentially about as close as you can get to a square wave output.
Yeah.
So it does this. Okay. It lights up and dims down in very little time. So it gives you nice spikes. I think these are in the microsecond range. So either you can pan the camera, or you can move the light source. It doesn't matter. But it should be moving so that then you can pick up the individual images. Now, because it's flashing 100 times a second, obviously measuring times that are less than 100th of a second is not too practical. But you can get to 50, in which case you get 2 flashes, right? So you'll see how this works, I think, on Wednesday. And I'll send you some stuff that's related to this. So you look on your email. Any questions? What you can bring any. I think any camera will do. A tripod would be useful because you got to swing these things. You got to hold the camera up. A medium focal length lens. Kit lenses will work fine because we're not talking precision. We'll improvise.
If you want to see the difference, I have a micro four thirds camera without a
Oh yeah?
Yeah. One of the newer mirrorless.
Oh really? Oh, okay. Oh, you can try that. Because
Actually does it in line, it does it all at once.
you can do that. It's sort of a learning experience. Because there's no need to calibrate. They're way too high. Do this because I haven't seen it. And you'll see what the other people do. So that's fine.
Yeah, explain to him, because I can't, I don't know what.
Micro four thirds, mirrorless system camera. No shutter, no mirror,
There you
no
go.
viewfinder. It's like
Well,
halfway
I think
between
there
the.
has to be a shutter bed, and
No.
so cameras work.
There's no physical shutter.
So just as the sensor?
Yeah.
Okay.
It's like halfway between a point and shoot and an SLR. I love it.
As I told you, that's very excited.
They're tiny. It's I can use my old lenses on a modern digital camera with an adapter without messing with the focal length.
Is that the cameras that take C-mount lenses too?
You can get you can because they have the flange distance is very short. So whenever you add an adapter to it, it just puts it at the proper distance.
That's why people are looking for C-mount lenses. I guess.
Because the C-mount adapter is like it actually recesses a little bit into the camera, and it's perfect. And see, my lenses are really cheap.
Well, yeah, unless they're Bolex sweethearts.
Yeah. Because I have all my old little film lenses that I use
Okay.
with the adapter.
Alright, maybe I'll see you tomorrow and the day after.
Hey,
All
hey,
right.
you forgot your chair for
See if I can get them.
It's good to see you.
Yeah. I'm gonna enjoy this. I'm glad I managed to catch you while you were still teaching.
Yeah.
A big disappointment of like last week.
Hey, your father friended me.
Yeah, my dad's a good guy.
That's good. That's all right. All right. Take care, guys.
Bye.
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 Oh, someone else forgot a chair. On the floor. Salute, everybody.
Bye-bye. Hey, thanks for dropping in.
There you go.
Thanks for dropping in.